Thanks everybody for sticking around. I know it's been a long weekend. Not literally, but figuratively. So hopefully you're all still with me. 2 talks left to go. Somebody is. All right, so who's this jerk on stage? My name is Darren Kemp. I do security research for Duo Security's Duo Labs team. If you don't know Duo, we do 2-factor authentication, and our labs group does proactive security research. I'll note quickly that I did this research with my colleague Mikhail Davidov, who deserves a lot of the credit. He's not here today, but he's an equal partner in all of this. So what the heck am I talking about? I am talking about the Windows WOW64 subsystem, which I will detail in a bit. And I am demonstrating a mostly simple EMET bypass using that subsystem. Can I get a show of hands who knows what EMET is, or if anybody's deployed or used it? Okay, if you don't know what it is, I'll mention that in a bit. And if I could also get a show of hands, who's got like some exploit development experience or knows like what like return-oriented programming and things like that are? Okay, a few of you. So if you don't worry. I'll also note that this research, we figured it would be a blog post, and then it became a 19-page paper. And now I'm trying to crush a 19-page paper into a 30-page or 30-slide presentation. So we'll see how that goes. All right, so just a quick refresher. x86 64 chips, which is what most of you are running in your laptops these days or on your desktops, execute in one of 2 modes. Long mode, which would be a 64-bit operating system, and legacy mode, which is how you run a 16 or 32-bit operating system. When you're executing in long mode, there's also the compatibility submode, which allows you to execute 16 and 32-bit pieces of code. So Windows on Windows is the WOW64 subsystem is how Windows executes 32-bit software on a 64-bit operating system. This is what keeps all of your 32-bit things running. It's largely transparent to the applications that are executing in that environment. However, you can programmatically determine whether or not you're running inside of it. It does have implications to how the registry behaves, how file system I/O works, exception handling, and how system calls are dispatched, which is probably the most important thing for this presentation. And it is absolutely holding back system security overall. So there's a lot of prior work dealing with this subsystem. I'm absolutely not the first person to tackle this, and certainly won't be the last. The closest presentation related to what I'm talking about today is the first one, Why User Mode Hooking Sucks, Bypassing Komodo Internet Security. In 2003 at CanSec West in Vancouver, there was a presentation on bypassing ASLR and data execution prevention using an artifact of how this subsystem works. Really elegant attack, which is now defunct. There was a presentation at Source Boston this year on developing interesting ROP gadgets that abuse the WOW64 subsystem. At least that was part of the presentation. And then a presentation at Source Seattle on obfuscation to defeat static analysis using cross-mode coding, which is a super long presentation name. It beats mine. But the point here is that switching between modes can confuse a whole bunch of static analysis and dynamic analysis tools. And of course, there's a ton of different blog posts on how this subsystem works and different ways to abuse it and weird things to do with it. So why does this matter? We took a look at some real-world authentication data talking to our service. I can't share the full numbers with you, but I can assure you they're sizable. 80% of the browsers, based on the user agent authenticating with our service, were 32-bit processes running on 64-bit versions of Windows. So let's think about this a little bit. The year is 2015. The first x86 64 chips were released by AMD in 2003, and 80% of browsers are still 32-bit software. It's kind of a sad state of affairs. And of course, 16% of those were actually just pure 32-bit, and 4% claimed to be 64-bit processes. So why is this valuable to attackers? I kind of briefly mentioned this. So there are some subsystem idiosyncrasies in the past that have decreased overall system security. That was the CanSec presentation that I was talking about. When it comes to developing ROP chains, you're limited to what instructions are available to you. You know, by switching modes, you get a different interpretation, so you've got more potential ROP gadgets available to you. Anti-emulation and obfuscation opportunities, right? So when I say anti-emulation or obfuscation, think about things like a piece of shellcode that does a pivot to 64-bit mode, decodes with an 8-byte XOR key, and then pivots back. Stuff that really trivial emulators are not going to handle well. And then, of course, the focus of this presentation is on bypassing hooks in protected mode code, which I'll get into in a little bit here. So some high-level internals. The subsystem is implemented entirely in user mode. There's no support from the kernel. All WOW64 processes have 4 64-bit modules in them. The first 3 obviously make up that subsystem, and then the 4th being a 64-bit copy of NTDLL, which contains all of your system calls and things like that. So the WOW64 DLL is the subsystem entry point. It's responsible for marshalling system calls, exceptions, file system, and registry redirection. That's the big one. The second is primarily there to support mode switches, saving CPU context to and from 32 and 64-bit mode. And then the WOW64 Winn DLL does additional marshalling for windowing and console subsystems. The details of how those behave isn't too important for this presentation, but I'll let you keep that in mind. And then, of course, there are 32-bit copies and 64-bit copies of important system management structures. So each thread has a 32 and 64-bit copy of the thread environment block. There's a 64 and 32-bit process environment block, and then there's 32 and 64-bit stacks and heaps. I'll let this slide ride for a little bit. I stole this from a Microsoft presentation, but this is sort of how the different components interact. So at the top, you've got kernel mode components, and at the bottom, you've got user mode components. As you can see, all of the interaction proxies through WOW64 and pops out at the end at NTDLL, with the exception of the windowing subsystem. Little liquid courage. All right. So this is what things look like in memory. This is important for the exploitation stuff I'm going to demo. So the TEB and the PEB are at fixed offsets from their 32-bit counterparts. So despite being subject to address layout randomization, or ASLR, if you can find their 32-bit the 32-bit structure, you can find the 64-bit structure. On Windows 7, all of those modules I was talking about, the load order is fixed. So again, they're subject to ASLR, but if you can find one of them, everything is going to be predictably aligned from there. Additionally, the 64-bit copy of NTDLL is always located in address below 4 gigabytes, and it is at a fixed offset from the 32-bit copy of NTDLL. This particular factor was big in being able to make this exploit work easily. On Windows 8, this is not true. Whether or not this is an explicit mitigation or just an architectural change Microsoft made, I don't know. But it's much more difficult to pull this off on Windows 8. It's definitely possible, but that load order changes, and the copy of NTDLL 64 is always mapped in an address above 4 gigabytes. Okay, so long mode transition. So how does this stuff switch back and forth? Windows uses 2 special segment numbers, hex 23 for 32-bit and hex 33 for 64-bit, to switch between modes. And this works with overlapping code segments. So a code segment is determined whether or not it's 64 or 32-bit by the L bit in the segment descriptor. If it's set, it's 64-bit. If it's not, it's a 32-bit segment. All of these transitions are generally invoked through a far jump or call. So as you can see here, this is the function that is typically used to transition modes. And you'll see the hex 33 at the beginning, so that's the special segment number. Anything after that branch would be executed as 64-bit code. So system call invocation. So if you think back to the diagram I just showed you, this is sort of what it looks like in code. It's not the complete process, but you can see there is a function pointer inside the thread environment block. So a call is made to that function pointer, which switches modes. And from there, there's a bunch of plumbing that basically deals with the different calling conventions and converting arguments and so on and so forth. But that all ends up, proxying through to the 64-bit copy of that system call. After you switch modes, you get access to the higher order registers. This is not necessary for pulling this trick off, but it's useful, especially on Windows 8 or 10. The higher order registers contain a lot of useful information that will help you gain context after you transition modes. So this is really good if you need to do continuation of execution with your exploit or repair program state. But like I said, it's not necessary for everything. So bypassing hooks. So this is the meat of things. First and foremost, this is a pretty old trick. Like, this concept dates back to like the NT virtual DOS machine and like old versions of Windows NT. This is not really a new idea. I'm just putting a new spin on it. The key here is that anytime you have some sort of security tool like an antivirus or something like that, they're going to want to hook functionality inside things like NTDLL, because this is where all your low-level functionality happens, right? Module loading, creating new processes, all of the things that attackers like to abuse. The 64-bit copy in a 32-bit, or in a WOW64 process, I should say, is often difficult or impractical to hook for a variety of architectural reasons. This has been used in the past, as I said, that prior presentation I talked about, to defeat things like antivirus, but I'm going to do this in a shellcode payload, which can be a little bit finicky, but you can make it work in practice. So EMET. For those of you who don't know, EMET is the Enhanced Mitigation Experience Toolkit. It is a runtime exploit mitigation tool provided by Microsoft. What it does is inject a DLL into the process that you want to protect, and that DLL hooks a bunch of functionality inside NTDLL. It sets a bunch of hardware breakpoints. It does a bunch of stuff to intercept and try and inspect things that exploit devs like to abuse. This will break most off-the-shelf exploits, like pretty much anything in Metasploit or something like that. You apply EMET to the process, it probably won't work out of the box. And the key here is that most of the mitigations use function hooks. And those hooks do not affect the 64-bit copy of NTDLL. So look, Mom, no hooks. So this is the 32-bit copy that has been intercepted by EMET. You can see that the function prologue has been overwritten by an unconditional jump. That jump lands inside EMET, where it does a bunch of additional processing to do sanity checks on the process. If it thinks that things aren't sane, it bails out. If you look at in the same process, the 64-bit implementation, which is what ends up getting called at the very end, there's obviously no hook. It's just a raw system call. So we got this to work sort of as a trial in a very contrived way, and we decided that we wanted to do this for real. Let's take a real-world vulnerability and see if we can do this. Turns out getting it to work with a real vulnerability is a little harder, but we got it to go. We took a Metasploit exploit that is obviously publicly available for a use after free flaw affecting Adobe Flash. If you guys think back to the Rust presentation yesterday, that was a dangling pointer example. Use after free flaw is a dangling pointer. So this is exactly the kind of stuff that he was talking about trying to prevent. I'm not going to go deep into the bug, but if you want to know more about it, there's really great analysis from both Core Security Technologies and Trend Micro. In order to make the exploit work, we only had to make rather minor modifications. We had to give it the ability to understand and parse PE32 plus modules, being the 64-bit version of PE files, which is portable executable, or the executable format Windows uses. And of course, we had to change how the ROP chain worked. So a little more on the original exploit. There was a really popular technique that was recently killed that uses, it sprays the heap with vectors, and then you smash the size of one of them, and what happens is you're able to use that to do an out-of-bound read. So you can use this as an oracle to defeat things like ASLR. You can read arbitrary process memory and figure out where things are. This is sort of the first stage of the exploit. It uses that to scan backwards through memory, looking for the header of the flash module in memory. And then from there, you can use the import and export sections to forward resolve other modules and other functions in memory to build your payload and to build ROP gadgets. It doesn't actually work on WOW64 processes out of the box. It's fairly easy to fix. It's just a broken gadget search. This is pretty much the bar these days for like a modern browser vulnerability, right? So you build an information leak so that you can understand the layout of memory. You discover your ROP gadgets, assemble your funky chain of things to disable non-executable memory permissions and stuff like that. You cause what's called a stack pivot, which means often you're taking control of an object that's on the heap, so you need to build a synthetic stack. Since you're on the heap, you often have at the time of crash, you have a register that's pointing to that location on the heap, so you use something like an exchange, ESP, ECX, or whatever register is pointing at your object, and you pivot the stack pointer to point at the heap, and then you build a synthetic stack. So usually your ROP chain does something like change memory protections. So it'll do like a virtual protect, change the memory permissions of your second stage payload, you fall into that, you do whatever nefarious thing it is you want to do, and then you resume the process. And as I said, the original exploit won't survive EMET. So return-oriented programming. We didn't have to change a lot in the original exploit. Instead of using the higher level like virtual protect function, you have to use, there's no kernel 32 or kernel base module in the 64-bit context. So you don't get all those convenient high-level functions. You have to use the low-level implementations, which tends to require a little more initialization and effort on your part. So instead of using virtual protect, you would use anti-protect virtual memory. And this right here is pretty much the crux. The entire technique is basically built on the redf instruction. And instead of like a normal function return, which would pop your return address off the stack when you return from a function, a far return will pop the code segment. So you start your ROP chain by popping the code segment off the stack, so that hex 33, and you pivot modes, and then you do everything off of the 64-bit copy of NTDLL. So this is sort of what the sequence looks like, right? You do the stack pivot, as I mentioned, you return into long mode, you do your reprotection of memory so that you can execute the shellcode you injected into memory, you fall into your second stage payload, theoretically you profit, and if you're not as lazy as I am, you actually repair the process state and make everything run nicely, which I didn't do because I'm way too lazy. Of course, it's never that easy. There's always a catch. So the first catch is symbol resolution. As I said, the original exploit scans through memory, resolves everything using import and export tables. None of those 32-bit modules directly import code from the 64-bit modules. So we need a way to find them. As I said, this is way easier on Windows 7. Remember how I mentioned that there's a static offset? Well, as long as you can leak or resolve the base address of the 32-bit copy of NTDLL, you can win, because all you have to do is take that address, subtract that hex value, and you'll find the 64-bit copy. On Windows 8, that won't work. You got to be a little more clever. So the second thing is payload development. Like I said, you don't have access to kernel 32 or kernel base, so you don't get all the convenient high-level Winn API functions you're used to. You can't do things like just call load library or Winn exec. You have to use their low-level counterparts. So LDR load DLL, NT create process. in order to make these work, there's a lot more initialization and stuff you have to set up, right? There's a lot more going under the hood when you call those functions, and we take a lot of that for granted. This results in bigger, uglier shellcode. In the case of a browser vulnerability, this isn't so bad because you don't tend to have a lot of problems with space to store things, right? It's not like you've got this small stack buffer that you have to keep things in. You've got a giant heap that you can stash everything on, but it does result in much uglier shellcode. So this is pretty much the C equivalent, the high-level approximation of what we built. I'll note that this is not doing all the proper initialization, as I mentioned. So where this would be a WinExec call, it would be literally one line of code. This isn't even complete. This is super hacky, and if you were to do this, as a real-world adversary, this is not how you would want to do it. But this works for a contrived example. All right, so I've got two VMs. One's just hosting Metasploit, and the other is a vulnerable system. And this will just execute an arbitrary command and run the calculator, assuming it works. Phew! Thank you. I was told not to put memes in my presentation, so I put memes in my presentation. Take that, Mark. Okay, so I didn't do this on Win 8, but we have a couple potential solutions. So those of you who are familiar with Windows shellcode development, you could do it like a more traditional payload where you do symbol resolution via the 64-bit copy of the PEB. You might have to do this in pure ROP. This is really vulnerability specific how you do this. So it really depends on the context you have in the vulnerability you're exploiting. Or if the vulnerability can be triggered more than once, you might be able to do something like build a 32-bit chain, depending on whether or not EMET would mess with you, that leaked contents of those higher order registers I mentioned earlier back, and then you built a secondary stage and then triggered the bug again. Again, this is all very vulnerability specific as to whether or not it would work. And alternative payload implementation. So I mentioned that you've got to write more complicated payloads. It's not as simple as one function call for a lot of things you would do. WOW64.dll actually has wrapper functions that encapsulate all of that functionality. The major problem is that they're not exported. So you have to indirectly resolve them. And a potential solution to that is there's a function called WOW64 system service EX. That function is exported, and it uses a giant jump table to dispatch all of those NTDLL functions. So you can probably do indirect resolution through that, but I haven't tested it. So in conclusion, EMET is significantly more effective on pure 32 or 64-bit processes. I don't want to play it down. Like if you're not using it, you probably should. You said it'll break most off-the-shelf stuff, but it works far better if it's protecting a pure 32 or 64-bit processes. WOW64 processes, less effective. And WOW64 strikes again. It's been the cause of multiple security issues, or at least multiple security bypasses. This is a classic case of legacy components impeding security, our desire for compatibility holding back enhancements to our software. This is an optional component in server core, so if you're not running 32-bit software and you're running a Windows server, you may want to make sure that that's not running. Of course, this technique does have limitations. I had to jump through a lot more hoops. It's a lot less reliable, which is frankly proof that you should probably be using something like EMET to protect processes from exploitation. And that's all I got. So, questions? It was 16.0.0 point something. It is in the slides. So, and it's also, I should mention, the full paper is available on this. So if you go to the Duo Labs website, you can actually read, the full explanation of how all this works. So all the stuff that I glossed over and kind of hand waved is better explained there. Yes, this is a vulnerability that's been patched for several months. So. Yep. Yeah. Yes. But I mean, the technique is you know, agnostic of vulnerabilities. It just happened to be a good vulnerability for demonstrating it with. Anybody else? Any hecklers? I have no idea. I mean, that's why I said I don't know if that change is an explicit mitigation or an architectural thing. But the reason, I mean, I'm sure more reverse engineering, I mean, it's a decent sized subsystem, so I'm sure more reverse engineering might reveal that, but I don't have an answer for you. All I know is it made my life easier. That's it. Okay, thanks guys.